Southampton, autumn of 1943. Rolls-Royce had just handed Supermarine the most powerful piston engine Britain could build, and it was ruining the best fighter Britain had ever produced. The Griffin was a monster. 36 liters against the Merlin's 27. Almost 2,000 horsepower where the Battle of Britain Spitfires had made barely 1,000. On paper, it turned the Spitfire into something that could catch anything in the sky over Europe. In practice, it tried to twist the airframe apart every time a pilot opened the throttle. Push the power up on the runway, and the aircraft would swing hard enough to put a wingtip into the grass. Get her up to fighting speed, and she wanted to roll onto her back. Test pilots were coming down from short flights with their forearms cramping, and the reports they filed were the kind that get a project quietly killed. Everyone in British aviation agreed on the solution: bigger fin, bigger rudder, better pilot training. Something conservative, something that could be drawn on Monday and built by Friday, because there was a war on, and nobody had the patience for cleverness. Joseph Smith wanted to bolt 2 propellers onto the same shaft and spin them in opposite directions. His own engineers told him it was the worst idea he'd ever had. A gearbox that would never survive a hard landing. 200 extra pounds hanging off the nose of an aircraft already dangerously nose-heavy. Concentric shafts machined to clockmaker tolerances, being maintained by exhausted fitters in a muddy field in Normandy. The Ministry of Aircraft Production looked at the drawings and saw a maintenance nightmare wearing an aeroplane. Then that aircraft went down the runway at Boscombe Down without a single touch of corrective rudder, climbed away clean, and came back with a top speed north of 470 miles an hour, and a test pilot's report that used the word finest. This is the story of how the stupidest idea in British aircraft design ended up on the fastest Spitfires ever built, went to sea with the Royal Navy, and was still flying combat missions 5 years after Germany surrendered. To understand why the Griffin caused so much trouble, you have to understand what Supermarine had actually done. They had not designed a new fighter. They had taken an airframe conceived in 1935 around an engine making 1,000 horsepower and stuffed almost double that into the nose of it. The Merlin and the Griffin were both V-12s from the same company, but they were nothing alike in the metal. The Griffin was longer, taller, and heavier by around 600 pounds once you counted the accessories. It would not fit under a Spitfire cowling without a fight, which is why Griffin Spitfires have those distinctive blisters and bulges along the nose. It also, and this is the part that caught pilots out, turned the wrong way. Rolls-Royce had reversed the direction of rotation compared to the Merlin. Every Spitfire pilot in the Royal Air Force had spent years learning to feed in right rudder on takeoff to hold the swing. Now the swing went the other way, and it was harder. There are accident reports from 1943 and 1944 that read almost identically. Pilot opens the throttle, the aircraft yaws, he applies the correction his hands have learned over 400 hours, and the correction makes it worse. Wingtip into the grass. Undercarriage collapsed, in several cases worse than that. What the pilots were fighting was not one force, but a stack of them, all arriving at once. The most obvious is torque reaction, the plain consequence of Newton's third law. Spin a heavy propeller one way, and the engine tries to spin the airframe the other way. On the ground, that means one main wheel gets pressed into the tarmac harder than the other, which makes the aircraft turn. In the air, it means a constant rolling tendency the pilot has to hold off with aileron. Then there is the slipstream. The propeller does not throw air straight backward. It throws it backward in a corkscrew, and that spiraling column of air wraps around the fuselage and slams into one side of the fin, pushing the tail sideways. There is gyroscopic effect, because a spinning propeller is a gyroscope, and a gyroscope objects to being tilted, which is why the swing got worse the moment the tail came up. And at high angles of attack, there is asymmetric blade thrust, where the descending blade takes a bigger bite of air than the ascending one and pulls the nose off heading. On a Merlin Spitfire, all of that added up to a manageable nuisance. On a Griffin Spitfire, with a bigger propeller absorbing twice the power, it added up to an aircraft that some very experienced men did not want to fly at full throttle. The Mark 21 was where the problem became a crisis. This was supposed to be the definitive Spitfire, with a new wing, a stronger structure, 4 20mm cannon, and enough power to chase down anything the Luftwaffe had left. Supermarine had put serious work into it, and when it went to the Airfighting Development Unit for its service evaluation, the assessment that came back was close to an execution order. The handling was condemned. The recommendation was that the type should not be issued to squadrons at all, and that the Royal Air Force would be better served by continuing to build the older marks. For an aircraft with the Spitfire name on it, that report was a humiliation. It also arrived at the worst possible moment, with production lines being tooled, contracts signed, and an invasion of France being planned around the assumption that the Allies would own the air. The obvious fixes were tried, and each one bought a little and cost a lot. Supermarine enlarged the fin and rudder, which helped the directional stability, and added drag and weight at the far end of a fuselage that was already struggling for balance. They fiddled with aileron gearing and trim tab authority. They played with the elevator. Some of these changes genuinely improved the Mark 21, and by early 1945, the aircraft was cleared and did reach squadron service. But every one of those fixes was a way of compensating for the torque after the fact. None of them touched the source. The engine was still trying to roll the aeroplane, and the pilot was still paying for it with muscle and attention that he needed for shooting down Germans. Joseph Smith had been Supermarine's chief designer since R.J. Mitchell died in 1937, and he had spent 6 years turning Mitchell's single elegant idea into 50 different aeroplanes. He was not a showman. He had inherited a legend and kept it competitive against a German industry that kept getting better, which is a quieter kind of achievement than designing the thing in the first place, and probably a harder one. His argument about the torque problem was simple enough that it sounded naive. Stop trying to absorb the force. Cancel it. Put 2 propellers on the nose, one behind the other, on concentric shafts. Drive them from the same engine through a gearbox that makes them rotate in opposite directions. The torque one generates is equal and opposite to the torque the other generates, so the airframe feels nothing. The corkscrew the front propeller puts into the air gets straightened out by the rear one, so the fin stops being punched sideways. The gyroscopic effects cancel too, because you now have 2 gyroscopes spinning against each other. And there was a bonus that mattered as much as the handling. A single propeller absorbing 2,000 horsepower has a tip speed problem. To take that much power, you need either more blades, longer blades, or coarser pitch. And every one of those options runs into the same wall, which is that the tips start approaching the speed of sound and efficiency falls off a cliff. Split the load across 2 smaller discs, and you get the power into the air without the tips going supersonic. On top of that, the rear propeller works in air that has already been given a rotational component by the front one, and it recovers some of that swirl energy that a single propeller simply throws away. More thrust, less drag on the fin, no rolling tendency, no swing. Written down like that, it sounds like the answer to everything. The engineering, though, was ugly. You need 2 shafts, one inside the other, turning opposite ways at high RPM, sharing bearings and oil. You need an epicyclic reduction gear that takes 1 input and produces 2 counter-rotating outputs at slightly different speeds. You need constant speed pitch control for both propellers, and the control mechanism for the rear one has to reach it through the inner shaft, which is hollow and rotating. You need oil seals that hold pressure at the interface between 2 components spinning in opposite directions, which is exactly the condition seals hate most. And all of it has to sit at the very front of a fighter, adding weight to the worst possible station on an airframe whose center of gravity was already a problem. When Smith took the idea to a working meeting at Rotol, the propeller firm that would have to build the thing, the room did not applaud. "You're asking us to hang a marine gearbox on the nose of a Spitfire," said Frank Dovey, who had spent the previous 2 years on variable pitch mechanisms and knew exactly what precision cost in wartime. "Every gear in that assembly has to be cut to tolerances we normally reserve for instruments. We're not making instruments. We're making 400 units a month with women who were working in a bakery in 1940. The objections came in layers, and none of them were stupid. The weight penalty was around 200 pounds by the first estimate, which is a serious number on a fighter. Every additional gear mesh is an additional failure point, and a failure in that gearbox does not mean a rough-running engine. It means a propeller assembly departing the aircraft. Balancing was a nightmare, because you now had two rotating masses whose imbalances could either cancel or reinforce depending on their relative phase. Maintenance was worse. Changing a blade on a conventional propeller was a job a corporal could do on a dispersal pan with a trestle and a spanner. Changing a blade on a contra-rotating unit meant getting at the rear disc, which meant either specialized gear or a lot of swearing. And the Royal Navy version was worse again, because the Navy wanted this for carrier aircraft. Salt air, deck landings that arrive like controlled crashes, and a hangar the size of a squash court under the flight deck. If the assembly needed a workshop, it was not going to see. Smith's counter was that they were solving the wrong problem by trying to make the aircraft tolerate the engine. He had run the arithmetic on the alternative, which was accepting a Spitfire that lost time and altitude every time the pilot had to fight the controls instead of flying the intercept. 200 pounds of gearbox against 15% more usable thrust, and an aircraft that would fly straight without being told to. He thought that trade was obvious. Almost nobody else in the building did. The contra-rotating idea itself was not Smith's invention, and he never claimed it was. Patents for counter-rotating propellers went back to before the First World War. Rotoll and de Havilland had both been circling the concept since the late 30s, and there had been experimental installations on test aircraft. The Italians had flown one. The Germans had studied it. The concept was well understood and thoroughly documented, and had never once made it into a production fighter, for the same reason that a lot of good ideas do not, which is that the manufacturing was too hard, and the payoff had not yet been worth the pain. What changed in 1943 was that the payoff got worth it. Once you have 2,000 horsepower, a single propeller stops being adequate and starts being the bottleneck. Getting the ministry to fund it was a separate battle, and the ministry had reasons to say no that had nothing to do with propellers. By late 1943, the money and the attention were drifting toward jets. Gloucester was flying the Meteor. Frank Whittle's engines were maturing. Intelligence coming out of Germany was describing a Messerschmitt with turbojets that would outrun anything with a propeller on the front. There was a real argument, made by serious people, that spending scarce toolmakers and scarce alloy steel on the most complicated propeller ever fitted to a fighter was investing in a technology that was about to become historical. The counter-argument was the calendar. Jets were coming, but jets in 1944 had an endurance measured in minutes, engines that lasted 25 hours between overhauls, and a habit of flaming out if you moved the throttle too quickly. The war was going to be fought and probably finished by piston engines. The Fleet Air Arm in particular had no jet option at all, because nobody in 1943 knew how to get an early turbojet on and off a carrier deck safely. If the Navy wanted a fighter that could match American types in the Pacific, it needed to come from a propeller. The authorization, when it came, was narrow. One development installation, full instrumentation, a hard timetable, and a clear understanding that if the program slipped, it would be canceled and the resources handed to something conventional. The build took the winter, and it was miserable work. The reduction gear went through several arrangements before one survived the test bench. The final assembly used an epicyclic train, where the ring gear and the planet carrier drove the two output shafts in opposite directions, which is a neat solution on paper and a brutal one in a machine shop, because the loads on those gear teeth do not distribute the way a textbook says they will when the whole thing is being shaken by a V12 at 2,500 revolutions per minute. Tooth profiles were reground 3 times. Case hardening depths were argued over for a week. The shaft assembly was the part that kept people awake. An inner shaft passing through a hollow outer shaft, both turning at high speed in opposite directions, means the relative velocity at the bearing surfaces is the sum of the two, not the difference. Bearings that would have lasted 500 hours in a normal installation were being consumed on the bench. The pitch change mechanism for the rear propeller ran oil through drillings in the rotating inner shaft and out through a transfer seal, and the first 3 seal designs leaked badly enough to coat the test cell in hot oil. Balancing was done by hand, blade by blade, on static rigs, then again as complete assemblies. Each blade was weighed and its moment recorded, and the sets were matched so that no disc carried more than a fraction of an ounce of residual imbalance. Then the 2 discs had to be phased relative to each other, which nobody had a proper procedure for, so they invented one. By February, the assembly was on an airframe, and it looked wrong. That is the honest reaction of everyone who saw a contraprop Spitfire for the first time. The nose was too long and too busy, and the 2 discs standing close together gave the aircraft a blunt, aggressive face that had nothing of Mitchell's original elegance in it. On the ground with the engine running, the sound was wrong too. Not the familiar hard bark of a Merlin or the deeper note of a Griffin, but something layered and dense, with a beat in it from the 2 discs cutting the same air a few inches apart. Squadron leader Alec Rennick drew the first flight. He had 1,100 hours, most of them on Spitfires, and 18 months of test work at Boscombe Down after a tour on operations. He had also flown the standard Griffin Mark 21 and filed one of the reports that helped condemn it, which meant he had a very specific and very physical memory of what he was trying to escape. The pre-flight briefing on the morning of the first flight was cautious to the point of pessimism. Climb to 8,000 feet. Establish level flight. Work the speed up in stages, with a hard stop well below the aircraft's theoretical maximum. Watch gearbox oil temperature and pressure continuously. Any unusual vibration, throttle back and come home. The takeoff run was the first thing that told everyone something real had happened. Rennick opened the throttle steadily, with his right foot resting on the rudder pedal out of 6 years of habit, waiting for the swing that always came. It did not come. The aircraft ran straight down the center line as though it were on rails. He had to consciously stop himself from applying the correction his legs wanted to make. The tail came up without a hint of the gyroscopic lurch that every Griffin pilot braced for. She lifted off at a shade under 90 miles an hour and climbed away without a wing dropping. On the radio, he said only that the takeoff was normal, which was the most abnormal thing anybody in that control tower had heard about a Griffin Spitfire in a year. The climb was less encouraging. He was carrying more power than the numbers predicted for the rate he was getting, and the aircraft felt heavy in a way that had nothing to do with trim. 200 pounds on the nose was doing exactly what the skeptics had said it would do, and there was clearly some efficiency being lost somewhere in the assembly that the wind tunnel had not warned anybody about. Level at 8,000 feet, though, the aircraft was extraordinary. At 300 miles an hour, it flew with a solidity Rennick had never felt in a high-powered fighter. He rolled it left and right and got the same response in both directions, which sounds like a trivial observation and is not. Every single engine fighter ever built rolls better one way than the other because the torque helps in one direction and fights you in the other. This one did not care. He pulled into a tight turn at full power, and the nose stayed exactly where he put it, with no need to feed in rudder to stop it sliding. He wrote in his report afterwards that the aircraft had stopped arguing with him. Then he pushed the throttle forward. At 350, the vibration started, and it did not build the way normal vibration builds. It arrived. By 370, the instrument panel was blurred badly enough that he could not read the airspeed indicator directly and was estimating it from the attitude and the engine note. The control column was buzzing hard enough to hurt his hand. He said later that his first coherent thought was that a blade had failed and he was about to lose the front disc through the cockpit. He brought the power back and the shaking stopped almost as suddenly as it started, which told him it was not damage, it was resonance. The landing produced one more surprise. With the throttle closed, the 2 propeller discs together made an enormous amount of drag, and the aircraft came down like it had a brake on. Rennick had to carry power all the way down the approach to hold a sensible glide path, and he floated less than he expected. He got it down cleanly, taxied in, and shut down in front of a small crowd of men who had already heard enough on the radio to know that the morning had been half a triumph. The inquest happened that afternoon in the flight shed, and it was not a friendly meeting. The problem was that Rennick's report cut both ways, and the half that was good was politically useless. Nobody at the ministry was going to authorize a production change on an aircraft that flew beautifully at 300 and tried to disassemble itself at 370, because 370 was where the fighting happened. What had actually gone wrong took Smith's team about 10 days to establish, and the answer was in the geometry. The two propeller discs were mounted close together, and each blade on the rear disc was passing through the wake of each blade on the front disc. Every time a rear blade cut through the shed vortex of a front blade, it received a pressure pulse. At most combinations of speed and RPM, those pulses were just noise. But at one particular combination, the frequency of the pulses lined up with the natural frequency of the whole rotating assembly, and the structure did what structures do when you excite them at their resonant frequency. It amplified. The forcing frequency was a product of the blade counts and the rotational speeds. With 5 blades on each disc and the gear ratios they had chosen, the excitation landed right in the middle of the operating range instead of safely outside it. The fix was arithmetic, and then a great deal of handwork. They altered the reduction ratios so the two discs no longer ran at the speeds they had, which moved the excitation frequency up and out of the range the aircraft actually used. They increased the axial gap between the two discs by a small amount, which gave the front blade's wake more distance to decay before the rear blade hit it. And they reworked the blade twist distribution on both sets, softening the aggressive pitch change near the tips that was making the tip vortices so strong in the first place. That last change was the one that ate the schedule. Every blade had to be reprofiled and hand-finished, then reweighed, then rebalanced, then rematched into sets. The men doing it were working to thousandths of an inch with files and gauges, and there were a lot of blades. There was also a quiet argument inside the team about whether to keep going at all, and Smith won it on a fairly cold basis. The aircraft had already proved the central claim. The torque was gone. Nobody had ever seen a 2,000 horsepower fighter roll straight down a runway with the pilot's feet flat on the floor, and that was not a small result. The vibration was a resonance problem, and resonance problems are solvable because you either move the forcing frequency or you move the natural frequency, and there are only so many places for either of them to hide. The second flight went up in March. Rennick took off with the same wariness a man has the second time he gets on a horse that has already thrown him. The run down the runway was as straight as before. The climb was noticeably better, and this was the first evidence that the blade rework had done more than solve the shaking. The reprofiled blades were simply more efficient. He was getting the same rate of climb at meaningfully less power than the first aircraft had needed. He leveled at 10,000 and started working the speed up in the same stages as before. 300 was smooth. 320 was smooth. He said afterwards that the last 20 miles an hour before the number that had frightened him took a long time to pass through. 370 came and went, and nothing happened. 380. 400. 420. And the aircraft was steadier at that speed than most fighters were at half of it. He was flying with 2 fingers on the stick. There was no rolling tendency to hold off. No rudder to feed in, no vibration beyond the ordinary background hum of a large engine working hard. He put it into a dive and let the speed build past the point where compressibility effects normally start to make an aircraft feel strange, and the controls stayed light and the nose stayed where he pointed it. He came back and did what test pilots almost never do, which is get out of the aircraft and say something unqualified in front of witnesses. "That is the best airplane I have ever flown," he told the men on the tarmac. "And I include everything I have flown against." The measured performance backed him up. The full development aircraft, with the fully sorted contra-rotating installation and the Griffin running at high boost, was making better than 470 miles an hour in level flight at altitude. The Spitfire that had started life in 1936 at 360 was now more than 100 miles an hour faster and, in the opinion of the man flying it, easier to handle than the original. What happened next was less dramatic and more consequential. The contra-rotating installation did not save the Spitfire Mark 21, which by then had been rescued by more conventional means, and went into service in 1945 with a single propeller. Where it mattered was at sea. The Fleet Air Arm had a specific and vicious problem that the Royal Air Force did not. A carrier fighter takes off in a very short distance, at low speed, with the throttle wide open, from a moving deck, often at night, sometimes with a crosswind, and always with no room whatsoever to correct a swing. Torque on a deck launch is not a handling nuisance. It is a category of fatal accident. The Seafire, which was a navalized Spitfire, had a reputation for being difficult around a carrier even in its Merlin versions. Putting a Griffin in one made that reputation considerably worse. Contra-rotating propellers removed the problem at the source. The Seafire Mark 46 and then the Mark 47 carried them, and the Mark 47 in particular was a serious aeroplane. Griffin 87 or 88, folding wings, 4 cannon, and a nose with 2 discs on it. Deck handling improved to the point where the aircraft was no longer regarded as a menace to its own pilots. The Mark 47 also gave the whole story its ending, which is later than most people expect. In July 1950, 5 years after the Second World War finished, 800 Naval Air Squadron went into action off Korea, from HMS Triumph flying Seafire 47s. They flew ground attack sorties and combat air patrols against a jet-age opponent, in an aircraft whose direct ancestor had fought over Kent in 1940. Joseph Smith's mechanical nightmare, the contraption his own engineers had told him was unbuildable, was still flying operational missions from a carrier deck half a world away and a decade after it was drawn. The idea outlived the Spitfire itself. Once turboprops arrived, contra-rotation stopped being exotic and became the standard answer to the same question, which is what you do when you have more shaft power than one propeller disc can usefully absorb. The Ferry Gannet had it. The Avro Shackleton had it, and gave the Royal Air Force crews decades of a noise so distinctive that people who lived near the bases could identify the aircraft with their eyes shut. The Soviets put it on the Tupolev Tu-95, which is still flying today, still using 8 counter-rotating blades per engine, and is still one of the loudest machines humans have ever built. Not one of those aircraft was designed by someone who thought the concept was clever. They used it because at high power it is simply the correct engineering answer, and the only thing that ever stood in the way was the difficulty of building it. Which is really what the whole episode is about. The objections raised against Smith in 1943 were not wrong. The gearbox was hard. The tolerances were unreasonable. The weight penalty was real. The maintenance burden was heavier than a conventional propeller and always would be. Every criticism his colleagues made turned out to be accurate, and the design went ahead anyway, and it worked. There is a particular kind of engineering courage in that, and it does not look like courage from the outside. It looks like stubbornness. Smith was not doing something nobody had thought of. Counter-rotating propellers had been in the literature for 30 years, and everybody in the industry knew about them. What he did was refuse to accept the standard reason for not doing it, which was that it would be difficult, at a moment when everything else on the table was a way of managing a problem rather than removing it. The men who wanted a bigger rudder were being responsible. Their solution was cheap, fast, and low risk, and in the short term, it was the right call, and the Mark 21 did eventually reach squadrons with a conventional propeller and a bigger tail. But a bigger rudder is a tax you pay on every flight forever. It is drag and weight and pilot attention, spent continuously to hold back a force you have chosen to live with. Smith's answer cost more once and then cost nothing. That is usually the shape of the better solution, and it is almost always the one that gets called impractical in the meeting. The Spitfire that ended the story bore very little resemblance to the one that started it. Twice the power. 4 cannon instead of 8 rifle-caliber machine guns. A new wing, a taller tail, a longer nose, and 2 propellers spinning against each other in front of the pilot. Mitchell would probably have struggled to recognize it. But it was still fast, and it was still, by the account of the men who flew the last ones, delightful to handle, and it stayed in frontline service for 15 years, in a period when aircraft generations were being replaced every 3. Joseph Smith never got the recognition Mitchell got, and he was never going to. He died in 1956, still at Supermarine, having spent 19 years keeping another man's airplane competitive against everything the world could build. His name is not on the aircraft. It is on the drawings. But there is one thing about the contra-rotating Spitfire that is worth holding on to, and it has nothing to do with speed records or Korea or the 295. When Alec Rennick opened the throttle on that runway at Boscombe Down, and the aircraft ran perfectly straight, what he was experiencing was the absence of something. Nothing happened. No swing, no fight, no correction. For a pilot, it was the most boring takeoff of his life, and it was the whole point. The best engineering usually feels like that. You do not notice it, because the thing it fixed has stopped happening. Every Spitfire pilot before that flight had been holding rudder on takeoff, thousands of them, hundreds of thousands of times, and not one of them thought of it as a problem, because it was simply what flying a Spitfire was. It took somebody willing to be called an idiot in his own drawing office to point out that it did not have to be. That is the version of the story I keep coming back to. Not the top speed. Not the drama in the boardroom. Just a man looking at a thing everybody had accepted for a decade and deciding it was not acceptable, then spending a winter, a career, and a considerable amount of other people's patience proving it. The idea was stupid right up until the moment the aircraft flew straight.